All right, so we're going to be looking at now series and parallel circuits. So you have an understanding of hopefully the schematics and how to draw them, open, closed circuits, what a load or a resistor is. Now we're going to start looking at more of the math and applying Ohm's law, being able to use a multimeter. Old school Christmas lights, why one goes out, the all go out. Why in the newer stuff can you have one go out and the rest stay on in your house? Why can one light switch be wired to only operate one light and the rest of the outlets in the room stay on? Why does your crock pot, put too many crock pots when you have family reunions and it blows a breaker, yet you can split them up? So we'll look at all those things. It comes down to this thing of series and parallel. Those are the two main ways that we can connect resistors, devices, loads. Again, they could be anything in a circuit. You're going to see some terminology here. There's going to be a lot of kind of puzzle. If you think of these problems as puzzles, that's more what they are. The math is not bad because it's pretty much just applying V equals IR over and over. However, keeping it straight of how to deal with things in series or parallel is the tricky part. So I'll show you how I do it, and then we'll go from there. So you're going to have something called the equivalent or total resistance for a circuit in series. Find its current potential difference. So in other words, I want to be able to find the current and voltage drop across each resistor as we wire them. That will be the same whether it's in series or parallel. We want to be able to do that. We want to be able to identify whether things are series and parallel and apply Ohm's law to these. The final step after this lesson will be to combine series and parallel in the same circuit. Okay, so just to give you a heads up of kind of where we're headed. All right, so there's two main ways, as we said, parallel and series. Okay. Um, Let me give you a diagram and then we'll come back to these. Series, they're all lined up. If you, and we're going to try to do some analogies here, and we're going to talk about like traveling the turnpike and toll plazas and paying a toll. Imagine you're the charge, okay? If you're the charge or the car on the turnpike, you're going to have to go through resistor A or toll booth A, toll booth B, and toll booth C to get back to your buddies. After you deposit a little bit of energy here, a little energy here, a little energy here. So let's say it is $20 to travel the turnpike. Okay. Or actually, let's say it's $21. So you might deposit $7 here, $7 here, $7 here, and return for the total of 21. Equate to toll at to voltage. Okay. So you deposit a little bit energy here, a little bit energy here, a little bit energy here, you return with nothing left. And that's the idea behind a circuit. Now, if you break this circuit or this light bulb goes out, you can't get past there. There's no detour, there's no alternate route. Okay. You can't, there's nothing. And so every light bulb would go out. Now, another thing is if 10 cars go through this plaza, 10 cars are going to have to go through this plaza. 10 cars are going to have to go through this plaza. So if you think about that like current, all the charge is going to go through here. All the same charge is going to go through here. All the same charge is going to go through there. Now, parallel, now it's called parallel because generically when we draw it in schematically, they are parallel. They don't have to be, and that's the confusing part when you see an actual circuit. They're not always easy to identify as they are on paper. But again, as I travel, okay, as I travel along here, and the car gets to now this is like a toll booth plaza. So now I can go through lane 1, lane 2, or lane 3. If you go to Breezewood or any of the other big interchanges, you don't go through every plaza. I'm not going to drop $7 here, then back up, go through 7 here, back up 7 here. I'm going to deposit all my money wherever lane I choose and then move on. So not every car or charge in this case is going to go through A, through B, and through C. They're going to divide it up. Now, how are they going to divide it up? That's going to be based off resistance. More is going to go through the lower resistance. However, if it's $7 to go through this plaza, you're going to deposit $7 here. If you went in this lane, you deposit $7. If you went in this lane, you deposit $7. So your voltage drop will be the same across each one. Now let's say I eliminated one. Okay, light bulb burn up. I can still get through. Now, some things are going to affect. I'm going to have twice as much. I'm going to have more traffic through these two than I did because now down to one, two lanes. So my resistance is actually going to go up. Anything about that at the grocery store or anywhere else, less lanes open, it's going to take a little longer. Your voltage would still be the same because I still would pay the $7 whether I went here or here. Okay. So again, the analogy I like to use is thinking about like a turnpike. Okay, paying a toll. Okay, the money is equivalent to the voltage, the energy. Okay, the current or the traffic flow, the cars, is analogous to current. You want to think about this as being like a plaza or the grocery store with multiple lanes. This is a single lane road. And I think that'll help you as we go forward of keeping it straight of what's what in these cases. Okay. All right. These are just all going over exactly what I just said. So you have these. Um, the main questions we want to be able to answer, and you're going to have some a lab simulator, and you've already seen it, but I'll go over it again with you. What's going to happen when you add light bulbs, say in series versus parallel? Are they going to get dimmer? Are they going to get brighter? Are they going to go out? Okay. So those are the types of things we're going to look at. All right. So if you look at this, you have one resistor here, you have two resistors in series here, you have three resistors here. Okay. If I go to my simulator and I have two there, let's add a third. They're all in series. And they got dimmer. Okay. Now why? Well, for one, if you add another toll lane, a toll booth, you're going to slow traffic down. So your resistance is going to go up. And this happens to be a 9-volt battery. It has nine, it's going to take $9 to travel the turnpike. So I'm going to deposit less now here, less here, less here. The total's still going to be nine, okay? But it's going to be divvied up a little differently. All right. So some key things there. And again, you'll experiment with this as well. Now, in this case, what's going to happen if I add another one in parallel? Well, think about a toll booth plaza. Think about the grocery store. If you open more lanes, what's going to happen? Yeah, it's going to be easier to get through. So your resistance and your flow rate is actually going to go down. And so you're going to see your resistance decrease. So let's add another wire in here. Another wire in there. And another light bulb. Okay. And brightness really doesn't change. Okay. Because it's still going to deposit the same amount of energy. But notice what happened. They sped up. All right. So this would be analogous to our toll booth. Again, three resistors in a row, three light bulbs all in series. Okay, you're going to pay a little here, pay a little there, pay a little there. Okay, so in series, what we were going to find out is if you think about it, if you add more in a row, you're going to slow things down. So the equivalent resistance in series are going to add up. So if you have three, you're just going to add them up. And that'll give you the total resistance for that circuit. Okay. Now, if 10 cars go through this one, 10 cars go through this one, 10 cars go through that one, So the equivalent current, or what we call the circuit current, is going to be the same everywhere in series. So the current through one, the first resistor would be the same as two, as three. Okay? Now the voltage, again, if it costs the equivalent voltage, or most of the time you see it written as EMF, the battery is 9 volts. That's $9 to travel the entire turnpike. You're not paying $9 every time you go. Okay, you would deposit some here, deposit some here, deposit some here. And so you would see the voltage drop across one, voltage drop across two, voltage drop across three in this example, all add up to the battery voltage. Okay, so these are your general rules for series resistors. And if you had four, five, six, you would just keep adding it up. Okay. Now, when you get a plaza or in parallel, it's going to speed things up. And so the relationship's a little goofy. 1 over the equivalent is 1 over R1 plus 1 over R2 plus 1 over R3. So you add up the inverses, and then you got to take the inverse at the end to get your equivalent resistance. Okay. Now, if it's $9 to go to the turnpike, you're paying $9 in lane one, $9 in lane two, $9 in lane three. So the EMF, or the battery, okay, or the equivalent through that branch, is going to be equal across each one. You're going to pay the same deposit. The current is not going to be the same. Not every car is going to go through every lane. So the equivalent in that branch will be the sum of all of them through each lane. Okay? And so those are your rules for parallel. These are the two, this is the hardest kind of part of this, is to keep this straight of how resistors or loads behave in series versus parallel. All right. So I've given you all the notes, okay, but that's the general view. You have them all. And I think it's just easier if I take a look and work the problems out with you. That's a nice table summarizing what I just said. Again, that chart, or the page that I wrote on, is using kind of that toll booth analogy, but this is saying the same thing. Okay. All right. Now, step one. Okay. Step one in all these is to draw your circuit. Draw the circuit. Okay. Step two, make a table of all the variables of R1, V1, I1, R2, V2, I2. Okay. Step three, okay, combine the circuit down to one resistor. And that'll make sense here in a second. And that's what you call your equivalent resistance. Step four, work back and find all the missing parts. All right, so let's take a look at these. Again, just kind of show you how I do them and set them up. You have a 12-volt battery source, so this is your EMF over here, 12 volts. Okay. You're going to have a resistor 1, 2, and 3. And again, it doesn't really matter where you draw them on this, as long as they're all in series. Okay, I'm actually going to go to a smaller. So this is my EMF, or my equivalent voltage. I'm going to label this one R1 just to keep them straight. This is going to be 6.75 ohms. This is going to be R2 at 15.3. And R3 is 21.6. Now, it doesn't matter the order. You could have put them in any order. That's not going to affect the circuit at all. Now, I like to make a little table over here of everything I know. R1 is 6.75. R2 is 15.3. R3 is 21.6. Okay. And I'm going to put V1, V2, the voltage drop across 3, and then also I1, I2, and I3. And that's just the current through 3. That's the voltage drop across 3. Now notice I haven't even looked at A or B. This is how I set them all up. Now I need to break these apart down into one circuit. So what I want to get to is so that I have what we could replace it with one resistor and it act exactly the same. Now it's called the equivalent resistance. Now I write it as this: 1, 2, 3. That way it tells me I've combined these circuits. Okay, in series they add up. So if you add those up, you'll get 43.68 ohms. So I could replace all three of those resistors with this one resistor, and it would work exactly the same way. So this is what we would call my equivalent circuit. Now I start working my way back and find all the missing parts. Now I know the equivalent resistance, voltage. I need to find the missing third part. And you're kind of always looking for that missing third part. So you're going to use Ohm's law. Again, that's usually EMF, the equivalent current, and the equivalent resistance. So that's 12. That's 43.68. And the equivalent circuit, or current, sorry, through that is going to be 0.27 amps. Now, in series, if 0.27 amps goes through 1, it's going to have to go through 2, it's going to have to go through 3. So this is that last part. You start working your way back and apply what you can. So because they're in series, that tells me all three of these are going to be 0.27 amps. If 10 cars go through that, 10 cars go through this one, 10 cars go through this one. Okay. So now anytime you have two of the three pieces, you can go back to apply Ohm's law, P equals IR. And so that's all you're going to do. So for instance, 1, you're just going to use all the 1 values. So you use 0.27 times 6.75. Plug and chug to find the voltage drop. You get about 1.8 volts. For this one, you should get about 4.13. And for this one, you should get about 5.8. Now, the way to check yourself is that the total voltages should add up to your battery. So if I add all three of these up, I should get around 12. You're going to be off a little bit because of rounding. That's how I handle every problem. That way they're always the same. Now I can look at these problems, what they're actually asking me. Calculate the equivalent resistance. Well, that would be 43.68. What is the current in the circuit? That would be 0.27 amps. But knowing how to break it backwards and find all the missing parts is how you're going to answer every one of these questions. All right. So this one's very similar. Okay. I'm actually going to assign this one, and it'll be on a Google Doc for you. And then I'll come back with a later video and show you how to do number 2 here. Okay. All right. So let's look at one that's a slightly different, and that would be number 5 here. Okay. You have a resistor, it's connected in series with another resistor that they're not telling you this time. Okay. So You got your EMF, you have R1, you have R2, and you got your circuit. So your EMF, okay, is 4.5 volts. It's actually telling you the equivalent current is zero point 0.6 amps. We'll call this R1, which is 7 ohms. This is R2, which I don't know. So you got R1, you got R2, 7 ohm unknown. You got V1, V2, I1, I2. Now, if you broke it apart or broke it down into one, your equivalent resistance, I don't really know because I don't know the other one, but I do know the EMF is 4.5 and I do know the equivalent current. So I can use Ohm's law. So 4.5, 0.6 times that resistance. And so the equivalent resistance for this case would be 7.5 ohms. That tells me, because they just add up when they're in series, that this is 0.5 ohms. Now let's just work everything back, just even though it doesn't ask. What's the same in series? Okay, current. So this 0.6 is going to be the same here. It's going to be the same here. And then I can apply Ohm's law each time. So V1, I1, R1, and find the missing voltage, and then do the same thing for 2. And you should find 4.2 volts here and 0.3 volts here. And again, they should add up to your battery voltage, which they do. All right. So that's a real nice problem there. Just another missing piece to the puzzle, applying everything. Right. Let's take a look at an example of a parallel circuit. All right. So you have, again, draw it. So now you're going to have a branch. So this is your EMF, which, oops, wrong problem. Sorry. Let's move on. This is the one I wanted. So redraw that real quick. So I have an EMF here of a 24 volt source. We'll call this R1. Middle one is R2. Bottom one is R3. Again, that's just to keep them straight. R1, and again, it doesn't matter either, but we'll just go in order here. 4 ohms, 8 ohms, and 12 ohms. So again, I like to set it up the same way, nothing changes. Try to keep them all pretty similar. So V1, V2, V3, I1, I2, and I3. Now, when I break them down into one single circuit, they're in parallel, but I can still combine them and replace them with this equivalent resistor. I'm still going to call it 1, 2, 3 to tell me it's 1, 2, and 3 combined. This is still my EMF of 24 volts. Now, in parallel, this is where it's different. The equivalent is 1 over R1 plus 1 over R2 plus 1 over R3. And then you're going to take the inverse of that to find your equivalent resistance, and you should find out that it's 2.18 ohms, quite a bit lower than every other one. And that's one of the advantages sometimes of putting things in parallel. Now, to find the current through that circuit, it's all the same way now. So that should be EMF equivalent, and then R123. So 24, 123 is 2.18 ohms. And so the current going through that circuit is going to be 11 amps. Now, in parallel, so there's another difference. In parallel, you're going to break up the traffic. So 11 amps current coulombs per second, 11 coulombs per second is not going to go through R1 and 2 and 3. Toll booth plaza. 20 cars enter in, 20 cars aren't going through R1. The total is going to be that. So the total that's coming in and then coming out. So if you measured on these two dots here, let's say A and B, sure, you would measure 11 here and 11 here, but not 11 across just one of them. The voltage drop is the same. What you're depositing at each one is going to be the same. So the voltage drop across one to get back is going to be the same that enters in. So if it's $8 to travel the turnpike, you're dropping $8 no matter what lane you go in. So this would be 24 volts. This would be 24 volts, and this would be 24 volts. Okay, so it's a big difference between series and parallel there. Now you have two of the three, so you're just going to apply Ohm's law for each one. So say you're doing it for one. So 24, the current through one times its resistance, plug and chug, you'll get 6 amps. Do the same thing for two, you'll find it's 3 amps. And the same thing through three, you'll get 2 amps. And the total should come up to 11 amps, which it does. Okay. So similar in how you treat it, it's just the rules you have to apply slightly different because it's parallel. First difference is this, how you find the equivalent. And then the other difference is now the voltage is the same, not the current. Current is the same through series. Okay. The other problem that I will put on a Google Doc for you to do some practice is going to be this number 4. Okay, again, just work it out just the way we did. And that'll give you 2 examples of each one. If you have questions, make sure you ask. Make sure you send me an email or sign up for the help session that we'll do. But make sure you get some assistance. Again, I'll give you 2 problems to practice, and you're going to have a lab that you're going to be investigating this stuff with that lab simulation.